I'm going to show you how to calculate an equilibrium constant. To do any equilibrium problem, you need to have a balanced chemical equation. Here it's saying that we have H2S, which is going to equilibrate into hydrogen and sulfur. To balance that, we need a 2 in these places, and then all of these substances will be gases. Once you have an equilibrium equation, you can write out equilibrium expression where you put the products over the reactants. So we need to have hydrogen in the numerator and sulfur in the denominator, and then our coefficients become the powers. I think I said sulfur in the denominator. I also meant sulfur in the numerator, and then the H2S in the denominator. So that's our equilibrium expression. Then, since this says initially contains this pressure of gas, and then we can solve an equilibrium expression with pressures just like we can with concentrations. We just sub the pressures into the appropriate square brackets. But since it says an initial pressure, we're going to need to do an ICE table because we can only put equilibrium values inside of an equilibrium expression. So I need my ICE table, I for initial concentration or pressure, C for change in the pressure or concentration, and E for equilibrium values. Then we want to put the substances into our ICE table. I like to make it very clear where my reactants and products change because we do some different math depending on what side of the equation we're on. So reactants on the left, products on the right. We can assume that the product concentration is 0, and then we can also write down plus signs for the product concentration and a minus sign for the reactant concentration. It says that it initially contains 5 atmospheres of pressure for the H2S, and put that coefficient in as well. Now we know that the change in concentration is going to be stoichiometric to these coefficients. So we know that we're going to decrease by a quantity of some amount times 2, some amount increase times 2, some amount increase times 1. We can start to infer what that increase is because this time we have the partial pressure of S2, 0.010 at equilibrium. Since we know going from 0 to 0.01 was an increase of 0.01, that was the amount that was changed. We know that this is going to be 1x. This is equal to 1x, or 2x, and this is equal to 2x. So 1x equals 0.01, so therefore x must equal 0.01. Then this box has to be worth 2x, so 0.01 times 2 gives me 0.02. And then also, this is 2x, so this is also 0.02. 0 plus 0.02 gives me 0.02. Finally, 5 minus 0.02 gives me 4.98. One thing though that we can do is we can take advantage, take a liberty here, and find out how big is x compared to our initial quantity. Since 0.01 divided by 5, I'm getting 0.01 because that's a product concentration compared to an initial reactant concentration. Since this is less than 5% or smaller, this basically remains unchanged. The amount of decrease is so small, it's not going to come into play overall. However, since 4.98 really isn't a tough number to work with, it's okay to also subtract that. Sometimes these numbers for our product concentration are just so tiny that when we're subtracting them from our initial reactant concentration to get a decimal value here, the work just becomes so cumbersome trying to keep all of those place values and digits straight that you're more likely to make a mistake. Now that we know the expression equilibrium values, we can plug them into our expression. So Kp, which is what we're solving for, is equal to H2, so 0.02 squared times 0.01, all divided by, you can either run this as 4.98 or 5. They really end up becoming the same thing. We'll go ahead and run 4.98 squared, and that'll give us a number. Plugging these numbers in, we get 1.61 times 10 to the negative 7th, and we get 2 sig figs because of this right here, 1, 2. So 1, 2 place values, 1.6 times 10 to the negative 7th, and that's equal to Kp. If we were to go ahead and run the same math using a 5 here instead, the math won't change very much. 0.02 squared times 0.01 divided by 5 squared ends up giving me 1.6 times 10 to the negative 7th. So for all intents and purposes, after rounding, these two values are the exact same. Therefore, sometimes this 5% rule, less than 5%, is really useful because it makes our math simpler. 5 is an easier number to use than 4.98, even though 4.98 isn't that difficult. Thanks for watching, and good luck.